Use our speaker, Professor Katia Bertoldi. Katia comes to us from Harvard University. Well, unfortunately she comes to us in a modern COVID electronic way, but that's better than nothing. Katia is famous for, I would say, many works redefining what we mean by the word material. And I am very much looking forward to her talk today. Please, it's all yours.
Thanks, Alexander. Thanks for the introduction. I hope you can hear me okay. Is that okay? Yes. Good, yes. Good. So thanks for the introduction. It would have been a pleasure to visit in person, but this is 2020, right? So we do what we can. Yes. So today, what I'm gonna tell you is about some recent projects in the lab about multistable structures. So let's get started. So the talk is about elastic structures, structure made of elastic materials. And this structure are known to go back, as soon as you remove the load, they go back to the initial configuration. And here you can see an example. This structure is made of rubber. And why is that? Well, the force displacement curve will be either non-linear, as in the case I said before, large deformation, but the potential energy has a single minimum, and typically it's in the undeformed configuration. However, it has also been known for a very long time that if you carefully design the geometry, you can realize structure with more than one stable configuration. Those are bistable or multistable structures. And here you can see an example. This is a thin shell, and it has a shape of a dome. And now you see that it's made of the same material used for the structure I showed you before. And now you see when we push it down, it remains there. We move away the finger and it remains there. And this is because, why is this? Well, in this case, the geometry leads to a multi-weld energy landscape. So you see the energy landscape now has two minima. And this minima might be at the same energy level, at different energy level. So for a long time, the community has known, a study how the geometry affect the energy landscape and how the geometry affect multistability. Recently, a new trend has emerged recently, where multistability has also been started to be exploited to design structure with new mode of functionality. And here you can see three examples. So, for example, bistability has been proposed to realize tunable lenses, structure capable of changing shape, and also small robot capable of swimming. Now, these three examples here come from different groups, from Chiara D'Araio, and from Doug Holmes at BU. But also my group has been thinking along these lines. And today I want to tell you about a recent effort on exploiting bistability to design deployable structure and on exploiting bistability to design machines that are capable of simple tasks, so robotic systems. All right, so let's get started. Let's start focusing on the first project where we have been exploiting bistability for designing deployable structures. So what are deployable structures? I think you're all familiar with those, right? So these are structures that have a compact state that is very suitable for transportation, for storage, but then they can expand it for functionality. And here in this picture, you can see an example. I believe, yeah, it was in New York City. And this guy here is Chuck Oberman, who's a designer, famous to design this type of system. Now, if you think of the characteristic that we would like this structure to satisfy, well, we want them to occupy minimum amount of volume when folded. We want the deployment to be autonomous, right? We also want them to be able to lock in place after expansion because we want them to be functional. And finally, if they are designed to provide an enclosed environment, we would like to provide some protection. Think about shelters, emergency shelters. All right, so in an attempt to realize structures that satisfy this requirement, two main strategies have been proposed. First one, linkage-based structure, and this is an example here in this picture here. So these structures are very popular, robust. They comprise basically linkages connected by hinges. And the deployment, what are the issue with this structure? Well, first of all, the deployment process might be challenging. You need to synchronize many components. This typically, is a challenge. And also this structure, I mean, in order to keep them in the expanded configuration, typically they require additional components. And another point is, you know, if you want them to provide a protective environment, you need to add a covering. So it's difficult to basically embed the covering within the structure. Other strategy that's been used is that are based on inflatable structures. So here you can see an example. And again, in this case, the deployment is extremely simple. You provide a pressure. And again, an issue is like if you want to keep them up, the pressure you should keep the pressure on. And another sort of issue is that the deployment process is difficult to be controlled, right? It's difficult to predict which part is popping up first. All right, so in my group, we have been looking at both family structures. We have been looking both at inflatable structure and linkage-based structure, and we have been trying to identify strategies to overcome some of the existing limitations. And first today, I tell you about our effort on inflatable structures, inflatable deployable structure, and then on linkage-based structure. So let's start with the bistable deploy, our project on bistable deployables, on inflatable structure. And this is an effort that has been led by my postdoc Ben, my student David, and it's in a collaboration with Chuck Oberman. All right, so for this project, what we've been looking at is, we've been inspired by is origami. And I believe we are all familiar with origami. It's the art of folding paper. And we have been sort of all use origami since we were kids to, you know, fold planes and boats. Artists have used origami to create beautiful sculpture. And more recently, also scientists and engineers have been, you know, exploiting origami principle to design deployable structures, so structures that can dramatically increase their volume. And furthermore, what is also being shown is that if you carefully design the origami pattern, this structure might be, you can make the structure multistable or bistable. And so our idea now, our simple idea has been, can we combine these two concepts to realize basically bistable and inflatable origami? So can we basically design origami that are bistable and inflatable at the same time? And this will be a platform. The idea is we can use this as a platform for deployable structure. So how do we go about that? First, we need a building block, right? We need a folding pattern. So our building block is extremely simple. It's a triangle. A, B, C are the vertices, alpha, beta are the angles. And now, you know, we want to deploy this triangle, right? So what do? We rotate this triangle around the edge BC. You see here. Now, an interesting feature is the following. It's a very simple geometrical property. So if beta is within this interval, what happened is that the vertex A intersect again the circle circumscribed to the initial configuration in basically in the projected view. And why does it matter? Well, when the vertex A intersect again the circle, it means that the angle alpha is recovered in the projected view. All right, simple geometry. But now this simple geometric concept provides a base for us to realize a bistable origami structure. Why is that? Well, I can use this as a building block. Now I can take a triangle and basically, you know, mirror it and then move it around. And for example, I can easily create a star-like structure. Now, what I know is that this structure will also have an expanded geometrically compatible configuration, because I know that for a certain deployment level, the angle alpha is recovered in the deploy space. So I know that the structure also has a deploy compatible configuration. All right, now I know I have a structure that has a flat compatible configuration, an expanded compatible configuration. What about everything in between? Well, in between, we know that any configuration in between is going to be geometrically incompatible. And we can easily quantify this geometric incompatibility. So here I use delta ABC to quantify this geometric incompatibility. So now, how can we move between the two geometrically compatible configuration? Well, we can take advantage of the flexibility that is intrinsic of any structure we're going to fabricate, right? Any structure we're going to fabricate has some flexibility, both on the faces and on the hinges. And now what we can use this flexibility, this compliance, to basically relieve this incompatibility. And the idea is also, so as I move through these two geometrically compatible configuration, the structure is going to be deformed, right? And this deformation caused by the geometric incompatibility is going to generate an energy barrier. And so at the end, what I expect to be able to realize bistable structure. Okay? So let's try to better understand how this geometric incompatibility vary. So here I pick a triangle, alpha 30 degrees, beta 50 degrees. And now what I can do, I can quantify the geometric incompatibilities, this delta ABC that you see, and now I can plot the compatibility as a function of the deployment height. And we see that basically the incompatibility is 0 in the initial flat state, and there is also an expanded state that is geometrically compatible, so compatibility is 0, and then in between it goes up and then it comes down. All right. So now somehow the idea is we can use this geometric incompatibility to generate an energy barrier, and so to make our structure bistable. But you remember, we want also our structure to be inflatable. So let's have a look at the volume underlying the triangle. And again, I can, simple geometry, I can explicitly determine this volume. And now here I'm plotting it as a dashed line, as a function of deployment height. And what do we see? Well, if we carefully look at these two curves, now we see that there is a problem. Why is there a problem? Well, the configuration with maximum volume occurs before, in the deployment process, is triggered, basically happens before the configuration, the expanded compatible configuration. So it means if I want to use inflation to move from the flat configuration to the expanded configuration, it's not possible, because I'm going to stop here at the maximum volume configuration. All right, so is this a universal property? Let's pick a different triangle with different alpha and beta. And now, here you see the corresponding curve in dark blue. And what we see that if for this case, the expanded compatible configuration occurs before the maximum volume configuration. So this structure now, this triangle can be deployed by inflation. However, we also see that the maximum compatibility and the deployment height are much smaller. And so somehow the idea is maybe this structure is going to be only marginally bistable. All right, so these were, so far we have focused on two triangles, but now, we have a simple geometry. We can very easily explore the entire domain space, the design space. And so here in this, what in this plot I'm reporting is the maximum geometric incompatibility for all possible triangles that have two compatible states. And now what we see is that if you want to maximize the geometric incompatibility, we need to be closer to the upper boundary. But now we want also to characterize inflatability, right? And for this, we introduce this inflatability constraint, I denote it with H, and pretty much the way we define it, we look at the deployment process in a space where I have the incompatibility on the vertical axis and on the volume on the horizontal axis. And now what I do, I calculate the arc length of this curve between the flat state and the maximum volume state, and between the flat state and the geometrically compatible state. And now what I want this ratio to be greater than 1. And so it means that I want the log to be greater than 0. And so now what I see is that where is this happening? It's happening close to the lower boundary. All right, so now we see that we're running into an issue, because what this plot are telling us is we cannot make a bistable structure that is inflatable out of a single triangle, because if I want to make it bistable, I need to be closer to the upper boundary, choose triangle closer to the upper boundary. If I want to make it inflatable, I need my triangle need to be closer to the lower boundary. All right, so a single structure made of a single triangle are not going to work. Now the question is, can we somehow combine different triangles to realize enclosed structures that are both inflatable and bistable? And this is what now we're going to try. So now what we're going to do, we're going to pick two triangles. And the first idea is we can put them side by side to realize this star type of structure. And then what we're going to do, we can do two layers and, put them on top of each other to create a cavity. Now, clearly, I cannot pick any pair of triangle, but this triangle should have the same expanded compatible height. They should also have an edge of identical length. And then, the angle should be such that I'm able to close the structure. And then when I look at the triangle that satisfies this simple requirement, I see that if I want the structure to be inflatable, the triangle have to be are sitting next to the lower boundary. And we know that this triangle are characterized by low geometric incompatibility. Now what we can do, we can also predict the maximum incompatibility and the inflation constraint for many structures realized by combining two triangles. And what we see is that the geometric incompatibility decreases as a function when the inflation constraint basically increases. All right, now the question is this level of incompatibility that we can realize, geometric incompatibility that we can realize with the structure enough to make the structure bistable? So up to now it's pure geometry. Now we need to bring in mechanics, right? Because we need to go and fabricate the structure. And so what we do, we pick one of these design, the inflatable design with the largest geometric incompatibility. We go to the lab and we fabricate it. We 3D print the face and we use plastic sheet to realize the hinges. And now what we see is that, here on the right, you can see the PV curve. And what you can see is there is no signature of bistability. It's a monotonic. The pressure keeps increasing as a function of volume. And you see also in the movie that is playing, when we detach the pressure from the structure immediately goes down to the flat state. So this structure is not bistable. So it means that this level of geometric incompatibility, given our fabrication process, is not enough to generate bistability. All right, what else can we add? Can we do? Well, for example, we can just, a simple adjustment is instead of connecting long edge to long edge, we can connect the long edge of the triangle to the short edge of the other triangle. Requirement is pretty much the same. And now what's changing is, you see, the domain from which I can choose the triangle to make inflatable structure is expanded. And this, when we characterize many structures realized by combining triangle in this way, we see that now the maximum incompatibility, we can increase the maximum incompatibility, geometric incompatibility. Now, is this enough? Let's go to the lab. We can go to the lab, fabricate the structure here denoted with B. And now what we see here in red, you can see the corresponding PV curve. And now you see the curve is qualitatively very different from the one we got before. And now we see that we have a region of negative pressure. It means our structure is bistable. And now you see David moving around the structure. Even after we remove the pressure, we open the valve, the structure remains in the expanded configuration. All right, so now we have a winning strategy. We have a strategy that works. But is this the only possibility, right? Now we want to use this. The idea is we want to realize functional deployable structure. And now we are left with this star-like shape that doesn't seem to be very functional. What else can we do? Well, for example, now we compare, up to now we have been pairing triangles side to side, but we can also pair them up and down, right? Paired by the face. And now the criteria are similar. We need the triangle to have identical compatible height. We want the edge to have the same length. In this case, the closing requirement is different. The two angle alpha for the two triangles have to be identical. And now what we see when we do this, we further expand the space from which we can pick triangles. And now, when we then we use a geometry to basically predict the performance, the geometric incompatibility and the inflation of all the structure we can build, we see that we can realize structure with even larger geometric incompatibility. And so, since structure B was bistable, we expect this structure to also be bistable. So let's go to the lab, fabricate one of the structure, and now here on the right you can see the PV curve, right? Again, we have a region of negative pressure, so the structure is bistable, and you can clearly see here, right? We remove the pressure, the structure remains in expanded state. In this case, that's a wedge type shape. All right. So we have another strategy that works. Up to this point, we always started flat. We started flat, and then somehow we deploy. But now what we can do, we can also think at the initial triangle in the XY plane as the projection of an initially rotated triangle.
Excuse me. There's a question in the chat from Tabasco, which is how does the presence of certain defects with positive or negative curvature at the vertices influence the bistability?
Good point. Good point. So honest answer, we don't know. So the model the model is purely geometric, right? So the model gives us geometric incompatibility. Then, we go and we realize in the lab, and at that point, there are hinges, there are defects, and we are somehow in an early stage. We don't even have a mechanical model. The model we have so far is purely geometric. So the model doesn't give any indication about that.
Sorry, can I clarify my question? My question is geometric. My question is still geometric, in fact.
Okay.
Because when you make origami, depending on the number of faces that you join at an edge and the way that the angles sum up, you can have different positive or negatively curved defects at the points. And somehow thinking mechanically, the sort of strength of the instability that you produce should depend on the sign of that curvature.
Yeah, I see what you're saying. We haven't looked at that. We haven't looked at that, at the effect of that curvature at all. Yeah, I see what you're saying. Okay. Basically, you're saying it's not purely it's not purely geometrical, but there could be also this defect playing a role. We haven't looked into that. Yeah.
Okay, thanks.
And yeah, so in this case, if we start basically, we assume that the flat is initially rotated, then now what we have, we can go from basically one deployed structure. This structure should have two different deployed stable configuration. And when we use simple geometry to basically scan the design space, what we see is this structure have even higher geometric incompatibility. And then we can go fabricate one. In this case, you see it's not flat, the initial configuration, but then we can inflate it. And we see again the PV curve, there is a region of negative pressure. Again, is bistable. And all right. So now basically what we built sort of a library of bistable and inflatable building blocks. Now, the question is, how can we use this to realize functional deployable structures that are multistable and inflatable? And so, well, a first strategy that we explore is, we can use this building block, this shape, this library of shape that we identify as building block for more, for functional structure. For example, we can take one of these wedge type structure, we can pair it with another one, and then, we can tessellate. And when we tessellate, we can get an arch. And so the idea is now we should be able to create an arch that is deployable and bistable and inflatable. And does this work? So here you can see a movie. In this case, the structure is slightly larger than the structure I showed you before. So it's made of corrugated cardboard. We cut it and basically join them with double tape. And now we inflate it. And now you see Ben going there. It's going to go there and remove the input. So remove basically the pressure, the tube providing the pressure. And, the structure doesn't flat. The structure remains up, right? Doesn't go back to the compact state. And then, all right. So this is a strategy. Another possible strategy is we can use components of the different shapes we identify to build functional structure. And so, for example, we can envision to build a tent-like structure, both of a layer of design 1 and a layer of design 4. And the idea is, we can use a layer of this star-like structure to create the floor, and to create the livable space, we can use a layer of design 4. And this is what we did. So in here you see now we sort of created a sort of an inflatable shelter. So now you see David and Ben connecting to the pressure source. There is a pressure coming up. You see that the structure is basically deploying. And in this case, the structure, we have basically what we did, we trimmed the triangle, and now we have 3 layers of design 4, just to make the space nicer. And now an important feature, now David is opening the door, and the structure is not collapsing, right? The structure remains up. And why is this? Because the structure is bistable. And now we can connect it to the vacuum, and we can bring the structure, we can fold the structure back. And pretty much here is where we are with this project on origami, the inflatable and deployable structure. All right, so first project was deployable structure via inflatability. We have also been looking at using dynamic to basically facilitate the deployment process of linkage-based structure. And this is a recent work done by my postdoc Ahmed and my student Boli. And so here really the question we are asked is, can we realize linkage-based structures that can quickly deploy and that are still stable and locked into in place after deployment? And here we take inspiration, and our strategy is based on transition waves. What are transition waves? These are large amplitude waves that basically switch between that travel through multi-stable system and permit switching from one stable configuration to the other stable configuration. And somehow, if you want to visualize those, you can think of a domino effect, right? So where basically you have a sort of a chain reaction, and when one of the tile goes down, and then this triggers the other to goes down. And this transition wave are recently also been explored from the metamaterial community to basically, to manipulate the propagation of signal. And for example, here you can see in the example here, you see has been, in this case, you get unidirectional propagation, because if the two energy wells at a different level, then you can only go from the higher energy level to the lower energy level. And in the example here below, instead, this transition wave has been exploited to basically enable propagation over long distances. And because you can basically harness the energy release upon snapping back by these elements to overcome dissipation. And here our idea is to basically exploit these waves to facilitate the deployment process. And so now here what you see is a very simple 1D linkage. And our idea is, we provide an input to the left, and then this wave should go propagate through the entire linkage and should transform this straight line into a semicircle. This is the idea. And now this is the first realization. So you see we provide an input to the left, the waves start to propagate. We see that some of the elements start sort of snap, they snap and they curve, but then we see that also the wave at a certain point stop propagating. So why is that? Can we somehow, why does the wave doesn't propagate through the entire structure? Let's try to learn more about the structure. So what I show you, the movie I showed you before, is a very simple linkage structure. So what we have n rigid bars, and those are connected at the joint, at the end, and they're all. And what we did, we basically design the ends of the bar to allow rotation in the interval 0 theta. And because when basically they cannot rotate outside this interval because contact prevent rotation outside this interval. All right. So now we want a structure we want a multi-stable structure, right? Because we want to propagate this transition wave. So we want to go from one stable state to the other stable state. So, and for making the structure multi-stable, what we do, we introduce linear springs that connect next nearest neighbors. And now what we can play a bit with the location of these springs. So the springs go from the center of one linkage from one bar to the center of the next bar. And now we can play, we denote with D, the distance between the springs and the line connecting the hinges, the joints. All right. So now let's try to see how, let's try to understand how these springs affect the energy landscape of the structure. So first I choose D equal to 0. And now what we see in this case, then I plot the energy. And what I see is that if D equal to 0, the hinges are unstable for theta equals 0. There is only a minimum here, right? When theta equals theta, capital theta. All right, so the structure is not bistable in this case. However, if I somehow shift the spring from the line connecting the hinges, the joints, then I see that the joints are stable both in the flat configuration, the snap, and in the rotated configuration. So both for theta equals 0 and theta equals capital theta. All right, so now I have a structure with two energy minima. So I have a bistable building block, I have bistable joints. But then, then we make a chain, and we try basically we apply a perturbation. So we provide some energy. But then what we see, and this is a snapshot taken from the movie I showed you before, is that the waves start propagating, but at a certain point, it stops. After snapping, for the first four joint snap, and then the wave stop. Okay, how can we go long? Can we make this wave propagate longer? Well, what we can think is the first idea is, okay, let's provide more energy, right? So we can provide another, basically kick more when we provide the input. We see now things are better, so we go along, and in this case, we snap seven joints, but then we still stop. So you could say, okay, even more energy. The issue is like, if I provide more energy, I'm gonna break this structure. I'm gonna break the joints. So that's not really a good strategy. And this very experiment, we also have we also have a very simple discrete model. These are linear spring and rigid bodies. And the prediction match pretty well with what we see in the experiment. So now the question is, how can we modify somehow the geometry to realize linkages in which the transition wave initiated by low energy inputs, right, can propagate through the entire structure? And here is the solution, one solution we identified. So what we ended up doing, we changed the connectivity of the spring. So up to now, we have been using a nearest neighbor spring. Basically, the spring, we're connecting nearest neighbor links. Now, what we can do, we can use the spring to connect next nearest neighbor links. So, now the spring goes from link I to bar I plus 2. And importantly, what we figured out, this is a very important effect on the energy landscape of the joints. So now let's focus on joint I. And now here is the energy. I'm plotting the energy when I minus 1 is flat. So when theta, I minus 1 is equal to 0. And we see there are clearly two minima, right? So we see that joint I is stable both in the flat configuration and snap configuration. Very good. But now, assume there is a wave coming from the left. Now at a certain point, joint I minus 1 is going to snap. And when joint I minus 1 snap, what we see is that the energy barrier, it kills the energy barrier. So it kills the energy barrier, it makes joint I monostable. So it makes joint I unstable in the flat configuration. So it makes joint I to snap. So basically, the snapping, when we have a next nearest neighbor link, the spring connects next nearest neighbor spring, the snapping on one joint forces the next one to snap because it makes it monostable. All right, does it work? So here is the same experiment, but just what we did, we changed the way the springs are connected, and now you see that the wave goes all the way. And and here is simple, now we can simple image DIC, simple image, digital image correlation. We can track pretty much the rotation as a function of time, and now we see that the wave goes through all the entire structure.
Can I ask a question? Can I ask a question?
Yes.
What about robustness, though? Now, unless this is entirely straight, you can perturb it in the middle as you're transporting this or something like that, and then as soon as one of the thetas changes, then it starts, the whole thing starts snapping.
Yeah. So these are good points. So we haven't deeply investigated what you're asking for, but the structure we are making, they are far from perfect, right? They are not perfectly safe. So I would say for very small perturbation is robust. Then clearly, as the amount of perturbation increase, at a certain point, probably the effect is going to, it's going to break this propagation of wave. But for what I can tell you is for moderate level of perturbation is robust, because in simulation we are perfect, but in the experiment it is what it is, right? And we are not talking about, the experiment are not super accurate, I would say.
So for example, like the angle theta, where you switch from bistable to unistable, how far from 0 is it? Like, what is it?
Right now, for this case, it's 20 degrees. 20. For this specific structure, is 20 degrees the angle.
Okay.
There are all sorts of games you can play, because so this is also, all the angles are the same, right? It's homogeneous. So this, all linkages are the same. You could see, and the way we assemble the structure, they say the target was 20, but I would say it's oscillating between 4 degrees plus minus, because the way we laser cut and then we manually assemble. So, and there are imperfection coming in, but there are all sorts of games that you can think playing, right? Because you can intentionally vary, for example, the angle theta.
So Jared Schiffbauer in the chat asks a related question about introducing thermal effects, so thermal randomness to maybe trigger the wave or to modify its propagation.
Yeah, the point is, in this case, you need quite a bit of energy, right? And you see this structure is bulky. But yeah, clearly, this structure is bulky, is large. We are talking about a meter-long structure. Made,
Jared specifically asked, could you imagine making one that's small enough that
if you can go small, yes, and clearly, you need to reduce the energy barrier that is compatible with the energy you can provide by, thermal excitation. For sure. I mean, it should work. Then we haven't. So in principle, let's say, okay, all experiment we have done is this meter scale, centimeter scale, right? And then each link is centimeters, so you come up to meters. No, the numerical model, in principle, in our numerical model, what we have linear springs, and we have basically links with a given mass. No, I mean a rigid body with a mass. So when you scale down, then the energy goes down. If you scale down the energy, it should work. We haven't done specific simulation, but it should work. Does this answer the question? Good.
Yeah. I was actually specifically wondering the question because there's a well-known effect in these sort of periodic systems with a periodic kind of stability on the giant diffusion effect. It's well known in tilted periodic potentials. And I was wondering if a similar sort of effect would affect the propagation speed of a wave in a small system like this, or if such questions have even been really considered. But I think you've kind of addressed my question. At least it's a pertinent phenomenon.
Yeah, no, and we haven't considered, and I would say I'm aware of recent effort in the, let's say, metamaterial community where more and more systems have been proposed that exploit the propagation of this transition wave topological soliton, call it as you prefer, and that type of effect, as far as I know, have not been explored.
Thank you.
In this engineered system.
I have a different question here. I imagine you can easily modify the design of your system such that depths of energy, of both energy minima at zero angle and at maximal angle are exactly the same. Nevertheless, I think that having a domain wall between one state and the other is still unfavorable energetically. So this domain wall will want to somehow get out of the system one way or the other. So what would that system, there should be something like a soliton in your system. How does it work?
So, yeah, no, I understand what you're, so okay. When you were formulating the question, I was trying to understand how I could make the two energy were the same. For this structure, for this specific structure, is not clear to me. Well, we probably need to pre-stretch, because right now, the springs are not pre-stretched, the other are pre-stretched more. But we should be able, we should be able to figure out a way to basically balance and make them the two energy well to be the same. Then in terms of domain walls, the system we have been, this specific system we have been looking at is very small. I mean, we are talking about 9 units, right? We have been looking at a different study, much larger systems. And then, yes, this domain wall formation play a huge role because we see them basically forming this domain wall.
Okay. And do these domain walls move somehow, or they stay?
They move. So, I mean, again, two cases. So if the energy well are non-different, so if the energy well are the same, at a certain point they stop because of dissipation. In real system, they stop because of dissipation, because they don't have enough energy to keep going. So basically what you do, you engineer this domain wall into the system. If the two energy well are different, they can propagate through the entire system. So they travel through the entire system.
But if energies are the same, why does motion of this domain wall require any energy?
Well, no, the point is you still need to go over an energy barrier every time. I mean, I have two energy levels that are the same, but every time to reach the other, I need to go over an energy barrier. And the way, I mean, at the beginning, I provide energy, right, in terms of input to go over the energy barrier. The problem is after I snap few units, some energy is gone, it's dissipated, and then I don't have energy enough to go over the energy barrier.
I see. Okay, that's understandable. Thank you.
All right. Well, if there are no more questions, let's keep going. But please keep asking questions. It makes it more interesting. So yeah, and then so the way we have been thinking at these linkages, these are sort of components for deployable structure. And maybe at this point I figured out I was trained as a structural engineer. So I always try to connect this phenomena to structures. And so the idea is now we can look at this simple linkage that we're seen as a component of a deployable structure. And for example, you can think also, for example, you can ask, okay, how can I combine this 1D element to realize a dome, a deployable dome? And one, a very simple design is I can take 4 of these linkages, and now I can connect them right at one end. You have a 4-way connection here. And now the idea is that in order for this to work, however, the connection should first preserve integrity, right? You should keep these 4 legs together. But on the other, it's also another important point is this connection should make sure that the wave can propagate from one leg to the other leg. It propagates basically from one linkage to the other linkage. And to enable this, what we did, we basically added this additional spring here. So the role of these additional springs is to make sure that the signal propagates, to basically elastically couple also the 4 legs. And now here is, simple experiment. So now we have 4 legs connected by a rigid cross and 4 springs. And now we basically keep one end and we see one end basically snap to the curved configuration. And then we see also the 3 other legs. And so we started flat and now we sort of a dome configuration. And then the structure is clearly stable also in the expanded configuration because it's a multi-stable structure.
So just to make sure, the 4 side springs are just so you can control that it folds up as opposed to down, right? Or like why?
These 4 springs?
Yes, the square, yeah. Mm-hmm.
The square spring, without the square spring, it basically I'm kicking this leg, only this leg will jump up.
Ah, okay, sorry.
The other basically, the one jump up, the other 3 remain flat.
Okay, sorry, thanks.
So this one basically transmits elastic energy to the other. So yeah, this spring basically, they transfer the mechanical signal from one spring. They provide energy to the other leg to basically kick it out. Does it make sense?
Yes, thanks.
Perfect. All right. So this is sort of brings me to the end of this first part of the talk, where we have been, looking at how bistable concept can be used to design deployable structures. In parallel, what we have been looking at is also using bistability to design simple machine, or anyway, structures that are able to move, I would call them. And here we got really inspired, the inspiration sort of come from robots. And here you can see a very complex and very sophisticated machine realized at Boston Dynamics, and you see it can do all sorts of fancy tasks, right? It can jump, it can roll, it can run, all sorts of tasks. But now this machine, very complex, very complicated, very expensive also, if you want. And their complexity somehow in recent years has also motivated the search for much simpler and inexpensive machines that are still capable of performing simple tasks, grasping an object or moving around. And typically, to realize this machine, soft material, think of elastomer, dielectric elastomer, gels have been used. And here you can see 3 examples, right? We have a robot, and the first and the third one are fluidic, so they use pressure to achieve motion. The one in the middle instead use shape memory alloys. So, and you see in fact there are cable, basically electricity coming in to heat them up. Now, if you look at all 3 examples, what they have in common, there are multiple tubes and multiple wires coming in. And why is this? Well, because what you need, these machines somehow need multiple input to move, because you have multiple actuators integrated into a single machine. And then what you need to do, you need to basically sequentially actuate them in order to achieve a certain function. And And now a question we have been asking is, can we further simplify the structure, the design of this structure? Can we make them to, perform tasks, simple tasks with a single input? So, and mostly we have been looking at pressure-driven structures, so with a single input, pressure input. And so, two projects I want to present. So now, looking at the time, we are running, I see it's already 2:50. How do you want to do it? Do you want me to stop? Do you want me to go? Continue?
I think at this point, we want you to continue. It's just...
Continue? All right.
You watered our appetite, so...
Good. So what we have been looking at both instabilities, and that's the second project, and also transition ways. So somehow, make this system move around. So, and the first project I'm going to tell you is about how we can explore transition way, the same type of way we have been looking in the project I just presented, so in this case to achieve locomotion. And this is a project was led by my postdoc Mo and my student Bole. So, okay, we want to exploit again transition ways. So what we learn is that we need a bistable building block. In this case, the building block is different from the one I showed you before, but it's also very simple. What we have 4 rigid crosses connected by elastic shims that are at edges. And then to make the structure bistable, we had a rubber band. And now you can see here the structure is bistable. We, have this stable configuration and the other rotated stable configuration. And, here you are. So this is the energy profile that we can extract from our experiment. So by integrating the force, we do a uniaxial test and then we can get integrate the energy. And what we see the structure as 2 stable configuration corresponding to the 2 rotated phase separated by an energy profile. In this case, we see the 2 is symmetric, right? The 2 energy were at exactly the same level. And also in feature, what we see is like as the structure transition from one stable configuration to the other, it elongates. So it elongates and then it shortens. All right. So now we have our bistable unit cell. Now, we need, if you want to propagate waves, we need to create somehow a structure, right? We need to connect several of them. And so in this case, we connect 1, 2, 3, 4 of them by using again same plastic shims, so to create these rotational edges. And now let's see how this structure behaves. So here you can see a structure. We put 5 units arranged in a 1D chain. And now in this case, we couple this unit with hinges of length 4 millimeters. And now what we have here on the left, this guy here is a linear actuator. And what this actuator does, it brings the first unit from one stable configuration to the other stable configuration. And while doing this, what we see is that when this actuator brings the first unit from one stable configuration to the other, it also initiates a wave that sequentially switch all the units from one stable configuration to the other. All right. Does this work for any geometry combination? So now what we can do, we can build another structure, same number of units. In this case, what we do, we increase the length of the coupling hinges. And now, we do the same experiment here, the actuator, but now you see that the story is very different. So the actuator switch the first unit, the second one try to switch, but then it gets stuck. And, and the last unit remains there. It's at the rest. It's not affected at all. It doesn't see any deformation coming through. All right. So how can we, now the question is, how can we better understand the dynamic, the nonlinear dynamics of this simple system? So for this, what we do, we use we start with a simple discrete model. So rigid body, the crosses are rigid bodies. And then what we have linear spring to model the rubber band, and we have torsional spring to model these rotational hinges that we have. And what the first step, we can write down the discrete equation of motion. We can also numerically integrate them to obtain a numerical solution. On the other hand, what we can also do, we can take the continuum limit of this equation. And then, we can somehow manipulate this equation. And what we can show is that they reduce to Klein-Gordon equation, specifically with quadratic and cubic nonlinearity. And then, this is an equation we can solve analytically. So we get a Klein-Gordon equation with theta. And then, we get basically submit a solution in a kink solution of this form, which you can see here, theta. And then we can go back, and theta and u are connected because they're coupled, and we can also get the corresponding solution for u. And so at the end of the day, what this model tells us is that these pulses that, propagate in our system are transition wave or topological soliton with two components that are coupled together. So they have a rotational component and a translational component. So as the wave propagate, they rotate the unit, and at a certain point, they also deform them longitudinally. And is the first question is this model any good? So here, what I'm for 4 different, configurations. What I do, we are comparing experiment, the discrete model, so basically discrete equation motion numerically integrated, and this analytical model, and we can see good agreement for all 4. So the model seems to capture what's going on in the structure. And then the question here is, okay, now we have a system that support the propagation of these transition waves, good. So can we somehow exploit them, harness to achieve locomotion? And here the inspiration comes from a limbless locomotion of snakes. And what has been shown is that this organism without leg, in order to move, what they do, they have a contraction extension wave propagated through the body, and they combine these with the control formation of anchoring point, to basically increase local sliding resistance and to prevent backsliding. And here is our idea. So we can exploit the rotational component of this wave to locally modify friction and to generate anchoring point. And then this wave that we have, they also produce extension contraction wave, right? They also have a longitudinal component, and we can use that to generate these contraction extension waves. So how do we use the rotational component to manipulate friction? Well, a simple solution is the following one. We attach wheels at the bottom of our units. And now, when the wheels are aligned with the direction of motion, in this case for theta equals 0, the friction is going to be minimal. But as the wheels are at an angle with respect to the equation of motion, we expect the friction to increase. Does it work? So here is pretty much the same structure I showed you before. The only difference is now we have wheels at the bottom. Before the wave, the example I showed you before, the movie I showed you before, the wave was propagating, but the structure was not moving. Now we see the wave still propagate, but now an additional effect that we see is that basically the structure always moves to the left. And why is that? Well, here is the starting point, right? We have our structure. Each unit is sitting in a stable configuration. And then, what we do, we use the actuator, the linear actuator that here is highlighted in green, to basically to move the first unit from one stable configuration, to move the first unit to the other stable configuration. And now what we see is that as the first unit moves to the other stable configuration, the other 2 units are still rotated. And so they provide basically resistance against motion in the right direction. And so the first unit expands toward the left. Now, when the first unit reaches the stable configuration, the rotated stable configuration, the other 2 units are transitioning. But at that point, the first unit provides an anchoring point. So these 2 units cannot move toward the right. And so when they reach the other stable configuration, as a result, this entire structure has moved toward the left a little bit. And then, every cycle, we keep repeating this. Now, this was for our 1D structure, but now, we can also reorganize this building block to form 2D structure, in this case, a simple square, 2 by 2 units. And now, here in this case, we have 2 actuators. And now, by properly tuning the phase of this 2 actuator, we can get the unit to move straight or to turn left or turn right. And this is because by tuning the phase, we can affect the propagation of these waves through the system and ultimately affect the motion, the locomotion. And so here is where we are. So we are now exploring how waves affect the locomotion of this simple structure. Up to now, we are looking at very simple structure.
Can I ask a question?
Yes.
In this 2-dimensional example, I can't see. Are there little links between in the vertical direction?
Yeah. So these coupling hinges basically are both in the horizontal and also vertical.
Okay. Yeah.
Yeah. So basically, we have a linkage here, 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 and here. So all end of the crosses, except for the one arriving at the boundary, they are connected. Clearly now something, we were thinking of, but we haven't done. You could also think about creating defects, right? For example, removing one of these coupling hinges and try to see how this affect the propagation of these waves. Something that we haven't done, but we have been thinking of.
Okay. have you guys looked at, I don't know what the right metric would be, but I think it's energy efficiency to see if you're...
No, and no, I think it's not good. And look,
Okay.
I would be shocked if anything good comes out.
Right, because you're putting energy into the system to get it to switch, but you're also...
Look, we are putting energy, right? There are these two linear actuators. I mean, you know, and they're plug-in. You know, efficiency, I would say, we haven't looked, but you know, I would be surprised if something good comes out. I mean, you know, it's not going to be good. It's not going to be efficient.
Okay, wonderful. Thank you.
All right. So I have one more project, but we are doing quite poorly in terms of time. Probably it's 5-10 more minutes. What do you want me to go? Keep going or stop?
If you can give us just a summary of it.
Yeah, I can be very quick and just give you an overview of what we're doing. But we also know typically these soft machines that have been, you know, they've been becoming more and more popular, they're slow. And what are they slow? Well, it's most of the time pressure is used to actuate them. And these soft robots, and you know, you need to transfer fluid from, you know, from the pressure source to the actuator, and then you need to go fight against viscous forces. And as a result, I mean, they're slow. And so what we've been also trying to do is to exploit instability, to try, you know, to make a fluidic machine that, you know, that are fast. And specifically what we've been using shell snapping that has been studied by the physics community, by the mechanics community for a long while. And, you know, the idea is when a shell snap is a fast event. And associated to this fast event, there is also a release of energy. And so the idea is, you know, we can build a very simple machine, for example, by coupling two of, you know, spherical shells and then to form an inflatable cavity. And, you know, then we can play with geometry, we can change the width and the thickness, the depth, the material that we make. But, okay, but this, you know, we can run simulation, finite element simulation. And what we see is that the PV curve, the PV characteristic of these simple machines or these simple, you know, structures are non-linear, and they're features that very qualitatively identical to that of a snapping shell. So we see clearly we have a snapping point, and the snapping occurs, it's a snapping at constant volume. And the idea is we don't need, when it's snap, we don't need to move volume around. This is going to be fast. And then we're also going to see that there is going to be a release of energy. And then, you know, we can fabricate in the lab, and we see, you know, good agreement between the finite element and the experiments. And then, you know, we can go and, you know, we can go and test them. And now, you know, we are inflating them. And what we see is that, you know, if you're carefully designing the structure so that it releases enough energy, we can make this simple structure to jump. And now the jump is not that much, but, you know, we can use finite element to optimize the geometry and simple finite element. So, you know, computationally very cheap finite element simulation coupled with a simple mechanical model to optimize the jumping height as a function of simple geometric parameters. And, you know, when we do that, so here is the initial design I showed you before, and this is the optimized design. And we can see that, you know, we can clearly, you know, improve sort of the performance. And, you know, and what is nice about this, when I was talking about soft machine, there was an example of, you know, as a simple structure, inflatable structure that was taking off. But that was based on explosion. And so, you know, you can take off one, but the second time is, you know, you need to basically reset the system. It's not that easy. In this case, an interesting feature is that it's very easy to basically reset. And, you know, you can take off multiple times. We just need to vacuum, and then we can jump again. And so pretty much this brings me to the conclusion. So I hope I convince you that bistable elements offer a promising platform to design a structure with new mode of functionality. And specifically, I've been focusing on shape changes, deployable structure, locomotion, and also rapid movement. And with that, here are the 4 papers. If you're interested in more details, here are the papers where you can find more details. 2 are out, 2 hopefully will be out soon. And that's all I have. So thanks for your attention. And please, if you have more questions, I'm very, very happy to try to answer them.
Thank you. Thank you. It was great. I am I'm particularly grateful that you gave your chapter about solitons, because this was exactly the answer to the question I was asking you before about two equal depths. I was asking about how to construct the soliton, and you replied to it. Very beautiful.
By the way, Alexander, if you're interested, so the structure you see at the bottom of this is also a bistable structure. I didn't present it today. I just like the picture. So also here, what we have soliton propagating through the structure to switch it from the expanded to the compact state. So what you see in this snapshot is a soliton propagating through the structure. It's a topological soliton.
Very nice. And by the way, I probably should shut up and ask if other people want to ask questions. Please, anybody wanted to ask questions?
Yeah, if I could ask sort of a follow-up question to my previous question. I definitely see the benefits of using bistability or snap-through structures when it comes to deploying structures quickly and then having them sit in their second stable state. Or similarly with the soft jumper, if you want something to happen very quickly. But when it comes to like cyclic processes, right? Like let's say you wanted locomotion to occur where you're crawling. You're more familiar with the physics than I am. I'm curious if there is any benefit to using bistable structures there.
Yeah, no, this is a very good point, and I haven't touched on it, and it's my bad. So this structure, typically when we operate this structure, the two energy well at two different levels. The two energy minima. And these come with certain advantages. So for example, you get unidirectional propagation for free because you can go only one direction, but come also with disadvantages that going back costs you a lot of energy. Right. So basically, there's sort of a directionality. So going one way is extremely easy because you release energy, and then, it's good. But then if you want to reset your system, you need to pump in energy, right?
Right.
And here, there is I'm aware of few groups that are now trying to engineer strategy to basically reset them. And what you can think of is, for example, harvest energy, use smart materials that harvest, magnetic field or whatever. Yeah, but you need to reset the structure, and the reset of this structure is an unsolved problem.
Okay. All right. Thank you.
Okay. Other questions, please. Well, while people maybe are thinking, I will ask you, I heard some talks and read some papers by Eti Efrati from Weizmann Institute in Israel, and his work is about non-Euclidean geometry of shells, which are flapping from one geometry to the other, pretty much the same way as in one of your movies at the very beginning. So do you know of any parallels between your work and his work?
Yeah. I mean, there are, at the beginning, I have a brief introduction. Yeah, so there have been beautiful work on this deployable structure. There is also beautiful work, by the way, from the French community by Joseph Bicot and Benoît Romain. In this case, an inflatable structure, they can get different non-Euclidean curvature by inflating them. So in our case, we were not so much, let's say, we had more of a focus on, I would say, functionality, and we went a different strategy. We went with origami. They went with basically, continuum surface.
Okay. And a related question, when in the first chapter, when you were constructing things of triangles, you avoided talking about energies, but clearly the height of the barrier between your two stable structures depends on the elastic properties of your material. In particular, it depends on the relation between sort of area elasticity and edge elasticity, which is...
I agree 200%. And I avoid talking about that because we haven't arrived there. So basically up to now, we have a geometric model, and now we start putting together, in terms of model, we basically, you can think about a very simple model where you have springs, right? You have springs at the hinges and you have spring at the faces, right? Because
Exactly, yes.
And clearly what we see is that mechanics plays a role, and it's fully understandable, right? Because depending on, at the beginning, we went through different strategies to fabricate the structure, and each of the strategy results in structure with different mechanical property, for the hinges, different mechanical property for the faces. And each of the, and for certain structures, an energy barrier is enough to get by stability, for other not. Clearly mechanics plays a role, and hopefully, soon we'll also be able to be more quantitative there. At the moment, our observations are fully based on experiments. We build something and then we see.
I see. I see. Okay. Any other questions, please?
So I was thinking about, actually, I was thinking very much about dimensionality, and you showed us one-dimensional structures that flex in 2 dimensions and 2-dimensional structures that move in 2 dimensions. I was wondering, is it possible to make a sort of a 3-dimensional cross element that dimension?
All right.
Just wanted to get rid of me. That was an assassination.
So yeah, so basically you're saying the cross, so basically extend this rotating square. The cross is based on the rotating square mechanism, right?
It's the skeleton of a cube.
Yeah, so basically to start with a cube. So the point is, if you just put the cube, the 8, right, crosses, it deformed purely in 2D. But
Right.
then there are all the tricks you can play. There is a beautiful paper by Martin Van Ecke. It's a Nature paper 2000. I can point you out to that if you're not familiar with that. But basically, you can somehow, by including an imperfection, so by sort of buckling, including the initial buckling, giving an imperfection, then you can play with these sort of things, and then you can also think about how do we assemble these different building blocks.
Right, and so the thought then is that you have an object then that could writhe in 3 dimensions as
yeah. So yeah, no, I agree. Experimental is going to be challenging. It's more challenging. Maybe that's the reason we have been, stay away from that. But yeah, fully agree.
Can I ask a question? Hi, Professor Bertoldi. This is Teng.
Hi, Teng.
Hi, yeah. So it's already very amazing. You can achieve so many functions using this bistable configuration. So I wanted to hear your comments about the advantage and disadvantage from going from bistable to multistable. I think now people can design unit structure with like more than 2, maybe 5 or 6 different local minima. And do you think some advantage if we can leverage the multistable to achieve more function?
I mean, it's a very good point, right? Our system are mostly all bistable. They are simple. Some of the origami are multistable. So if you remember the shelter, basically there are 3 different levels, but we never harness that. So honestly, all our design treat them as bistable, right? We never harness the fact that you can have more than 2 bistable configuration. I think if you think into as a robotic system, that might be, it's a big advantage if you're able to basically engineer more than 2 or 3, more than 2 shapes, because then you can, think to further expand, think about a gripper, right? You can think about resetting maybe that, right? So it's solved, and then you can reset instead just reset between 1 and 2, you can reset, between multiple states. If you think about wave propagation, I never look into that, but I think that also might be very interesting, because right now, we are going between 2, but then if you have 3 states, it might be interesting, because you might have wave that switch between 1 and 2, and the other going, you might have multiple waves propagating and interacting. So I think it would be fun. I'm interested in looking into that. We never look into that, but I think it might be an interesting problem.
Thank you.
Any other questions? Well, I feel that our audience is exhausted.
So does the speaker.
So does the speaker. Then let us thank the speaker once again. Thank you, Katia. That was wonderful. Thank you.
Thank you, guys. Thank you, everyone.
Thank you.
I'm going to stop recording.
Perfect.
Thank you. Bye.